Hi, today on Trigonometries, we're going to look at a problem from linear algebra. Specifically, we're going to look at a matrix and try to compute its eigenvalues and its eigenvectors. What we'll look for in particular are a basis for each of its eigenspaces. Alright, so here's the problem that we're going to look at. We're going to consider this matrix here. This is a computer algebra system called Maple, and you can do this by hand and follow along if you like, or in a computer algebra system of your choice. To compute the eigenvalues and eigenvectors of this problem, we need to first find the matrix A minus lambda I, where lambda is a real number. By I, I mean the identity matrix. So to form that, we're going to need the 4x4 identity matrix. If we compute that here, we get this guy. And then A minus lambda times I will be this matrix here. Now, where this matrix is not invertible is where it'll have a null space. And if it has a null space, the vectors in its null space will be the eigenvectors for whatever eigenvalues we find. To find the eigenvalues, we need to find the characteristic polynomial, which is the determinant of this matrix. So we'll take the determinant percent. Percent just means to use the previous output. So this produces this polynomial here in lambda, and that's called the characteristic polynomial. So this polynomial, in order to find the eigenvalues, we need to set it equal to 0. You'll notice that every single term has at least a lambda squared in it, and so solving this polynomial is not too bad. We can just factor that lambda squared out and then factor the resulting equations. But we happen to have a computer algebra system that can do a lot of that work for us. So we can avoid some of that by hand computation by just factoring this straight up. And this is the factored form of the characteristic polynomial that we get. The zeros of that polynomial you could find by just setting it equal to 0. Well, in that case, you set each factor equal to 0, and we end up with two possible eigenvalues. Specifically, lambda equals 0. Lambda equals 0 will make this factor equal to 0, so it's either that, or lambda is equal to 2, which is what would make this factor equal to 0. Notice that each of these factors have a 2 in the exponent. What that's referring to is something called the algebraic multiplicity of the eigenvalue. It's the multiplicity of that eigenvalue as a root of this polynomial, and that'll become important in a minute, so keep an eye on that. Both of these eigenvalues have an algebraic multiplicity of 2 because that's how many times that factor that corresponds to that 0 occurred in the polynomial. To find the eigenvectors, what we need to do is construct the matrix A minus lambda I for each of the eigenvalues there. So our first one will be A minus 0 times I, which will just give us the matrix A. And then we need to find the null space of this matrix, which we can do by row reducing it. So we'll do reduced row echelon form of this matrix. And we'll end up with this here. And you notice this has 3 pivots, one here, one here, one here. So these first 3 columns are pivot columns. This 4th column here is a non-pivot column. This is going to be the free variable column. And I haven't augmented this with it being equal to 0, but if you wanted, you could put a bar here and put some zeros on the side, and it wouldn't have affected it as we row reduced. But this is basically telling us then that x1 minus x4 is equal to 0, x1 plus x4 is equal to 0, and x3 minus 2x4 is equal to 0. Let's set the free variable x4 equal to t. In that case, the first equation here, which is x1 minus x4 is equal to 0, we can simplify that by replacing the x4 with a t and then solving for x1 by adding the t over to the other side. So we can get rid of this and we just find that x1 is equal to t. Similarly, x2 plus x4 had to be equal to 0, but we changed x4 to be t. And then moving the t to the other side, we find that x2 has to be equal to negative t. Similarly with x3, we have that x3 minus 2x4 is equal to 0, while x4 is really t. Adding the 2t to the other side, we get that x3 has to be equal to 2t, and then finally x4 has to be t. If you notice, we've kind of cooked up a column vector with all these t's in it. If you factor the t out of that column vector, you find that your x vector has to be equal to t times the vector 1, negative 1, 2, 1. And so this tells us that a basis for this null space has to be this vector here, which we'll call x1. 1, negative 1, 2, and 1. Every solution to a minus 0i times x equals 0 will be a multiple of this vector here. We can verify this by computing the null space of a minus 0 times I. And sure enough, we get a multiple of that. So the vector that we find here is precisely the vector that we found up there. I just kind of showed you how you do it by hand. Now, if we do the next one, we can find a minus 2 times I4 because lambda equals 2 was the other eigenvalue. Scrolling up here, you can see that there. So A minus 2I produces this matrix here, which we can do reduced echelon form again on to get this. And you'll notice this time we have a pivot there and a pivot here and 2 non-pivot columns. That means there's going to be 2 free variables or 2 vectors in that basis. Since we have 2 free variables, what we'll do is we'll let x3 be s and x4 be t again. And the first equation here says that x1 has to be equal to 0. The second one says that x2 minus x4 is equal to 0, but x4 we said is going to be t. So we can now add that t to the other side and we get that x2 is equal to t. x3 we said was s, and then x4 is equal to t. This time you can see that we have a column vector that has a t and an s in it. Separating this out into just the s terms and the t terms, we have that the s is going to multiply by a vector that has 0, 0, 1, 0 as components, and the t is going to be in here as multiplying a vector that has 0, 1, 0, 1 as the vectors. And so the 2 vectors that we should get out of this, we'll call y1 and y2, are going to be 0, 0, 1, 0, that's for the s, and 0, 1, 0, 1 for the t. And that'll produce these 2 vectors here, which we can check by looking at the null space. The null space is a little bit tricky to look at when it's 2-dimensional because it has to have the same span, but maybe we'll get lucky and it'll look the same. And sure enough, we do. It's in a different order, but it works all right. All right, so that we have here a basis for the null space. And so we can finish this off by making the following observations. We have that x1 is a basis for the eigenspace corresponding to lambda equals 0. This should have the property that when we multiply this by a, that we should get 0 times x1. That is, a x1 should be equal to 0 x1. That's why x1 is an eigenvector with corresponding eigenvalue 0. We can check that by taking a, which is still this guy here, and multiplying it by x1. We should get 0 times x1, which would just be the 0 vector. And sure enough, when we do this, we do indeed get 0, 0, 0, 0. The 2 vectors y1 and y2 form a basis for the lambda equals 2 eigenspace. And so we can check that. These guys should have the property that a y1 should be equal to 2 times y1, and a y2 should be equal to 2 times y2. So if we look at y1 and we compare a times y1, we should get the vector y1, which is this guy here, and then a times y1 should be twice that because of the eigenvalue thing. So when we do that, we indeed get, there's y1, and here's 2 times it, which tells us that a y1 is equal to 2 times y1, which makes it an eigenvector. Similarly, we have that y2, if we multiply that by a, we should also get twice that. And if we do, sure enough, here's y2, and when we hit it by a, it just doubles it. And so that's pretty much it. That's the idea. So we've got 2 bases here. We have for lambda equals 0, we have the basis x1, and for lambda equals 2, we have the basis y1, y2. These are bases for the eigenspaces corresponding to each of those eigenvalues for this matrix here. And that's the answer to this question. And that's it for today's episode of Trigonometries. If you have any questions that you might like to see answered on this channel, put them in the comments and we'll try to make some videos dealing with your examples. Otherwise, check us out next time when we do an example from another topic. And we'll catch you next time on Trigonometries.